1, 2, 3. Welcome everybody to another Friday seminar of the Institute of Computational Science. Today's speaker is Rebecca Bieri. Rebecca is well known to the Institute, at least to the older people here, because she did her undergrads at the University of Zurich. And I remember her when I was a PhD student. I was TAing one of her courses. I don't remember which course it was, but I remember she was one of the best. After her undergrad, she went to Paris to do a PhD under the supervision of Joe Silk. And after this, she went to Munich for a fellowship at MPA with working with Simon White and Volker Springel. And very recently, she came back here and she's now a postdoc again at this institute, working together with Ben Moore on the new Arrakis space mission. So it's a great pleasure to have her back and give a seminar. And the seminar is going to be about galaxies and feedback.
Yeah, thank you very much, Aral. It's very weird to be introduced by your old theoretical mechanics tutor, but here we are. So I'm very excited to be here and to talk about mostly work I've done in the last few years, 3 years at MPA. And so because we are not so many in the room, this should be really a discussion. So if you have any questions, please feel free to ask and we can have a discussion now during the talk, but also after the talk, obviously, at any time. Okay, so yeah, I'm going to talk today about what one of my main research interests, which is looking at how different feedback processes affect the life and evolution of massive galaxies, how exactly large-scale winds are launched and propagate through the ISM into the CGM. And I'm going to talk today about 2 different complementary approaches in looking at this problem. First of all, I will talk about idealized simulations of galaxies, of Milky Way type galaxies, where I resolve the multi-phase 3-phase ISM properly, and then how different feedback processes influence the structure of the ISM. And then later on, I will connect it to the large scale and talk about cosmological zoom simulations that treat the ISM in a very approximate way, but then allows to study how different feedback processes affect and interact with the multi-phase gas in the CGM. So first of all, why do we need any feedback processes? This is often motivated when looking at the galaxy luminosity function, which is shown here as the observed quantity, so this dotted line, and overplotted is the halo luminosity function, halo mass function, downscaled assuming a constant star formation efficiency. And so what you can immediately see is that in the observations or in reality, the star formation efficiency is not constant across all mass ranges, as in particular in the low mass range and in the high mass range. And so to understand this better, usually people invoke some kind of feedback processes in order to match for the theoretical models to match the observations. And so for this, in the low mass range, people often use stellar feedback or mostly supernova feedback as an important driver of these low mass galaxies that drive winds out into the CGM and with this influence the star formation within the galaxy. But there's one problem, because these supernova wind ejecta have roughly constant velocity. And so above a certain mass range, this velocity is not fast enough anymore to shoot over the escape velocity of more massive galaxy. And so we need a different type of feedback, a more effective feedback for massive galaxies. And this is often this is thought to be provided by AGN feedback coming from the supermassive black holes that are found at the centers of most local galaxies. So this picture is is a bit simplified, obviously. And so first of all, for many reasons, but first of all, it's simplified because stellar feedback, so supernova, but also radiation from the stars and wind from the stars, also happen in the massive galaxies. They don't not exist there, right? And they're actually very important in shaping the multi-phase structure in these massive galaxies, and also shaping the energetic structure of these massive galaxies. And this is then in turn again important in understanding the coupling efficiency of the AGN feedback and the launching and of these large-scale winds that then propagate out to the larger scale. And this is something I really want to motivate in this talk. The importance of also considering the stellar feedback and the different stellar feedback channels when understanding the evolution of massive galaxies. So what are exactly actually my scientific questions that I'm interested in and that I will talk about in this talk? So what I'm really interested in, as already indicated, is the different physical processes, how they affect the structure the structure and the energetics of the multi-phase gas in massive galaxies, how these different feedback processes actually locally couple to the gas, and how they then propagate through the ISM and launch large-scale winds. This is what I'm interested in, and this is what I'm going to talk about in the next coming time. So understanding the cycle of feedback is obviously complicated by the extremely wide range in space and time. So the feedback cycle, right? Like it starts locally around either the stars or the black hole that are formed in very small scales. These stars then, for instance, live in mostly molecular cloud or in very dense regions within the ISM. But then the ISM or the galaxy lives within the large scales where the outflow of these from these massive galaxies, but also the lower mass galaxies, then interacts with the multi-phase gas of the circumgalactic medium, but also in the inflowing gas that comes into the galaxy. So it's a really large range in space and time, and basically impossible to solve all at once. And this is why I'm using two different types of approaches of looking at this problem. First of all, idealized simulations, and second of all, then cosmological zoom simulations, but that then treats the ISM in a more approximate way. Why is it so difficult to simulate this large range in space and time? This is partly because the computational costs increases as resolution increases, mainly because of the dense and cold gas in the ISM. And many simulation approaches then solve this by imposing an effective equation of state that then solves for the gas instead of solving the individual gas phases within the galaxy. And this then has the result that the structure, the ISM structure within the galaxy, is very smooth, and also where the warm medium fills most of the volume. If you have seen any picture of the ISM, we know that the real ISM in the universe is somewhat opposite to that. It has a very non-smooth structure. It has a multi-phase structure where we have hot ionized, warm ionized, and cold gas, and where most of the mass of the gas within the ISM is in the cold, warm, and molecular gas. And this is also important, as I will stress later, in understanding actually the different coupling efficiencies of the feedback processes with the ISM, and therefore the launching of the large-scale winds. And so to understand this a little bit better, I started the SATIN simulation project, which goal is really to understand or study the effect of different stellar feedback, but also then AGN feedback outflows on a stellar feedback regulated ISM. So in the first part, I will then now talk about how these different stellar feedback channels influence the structure of the ISM, and why it is important actually to include various different feedback channels in order to understand and get the right multi-phase structure within the ISM. So what simulations do I do? I use radiative transfer simulations in order to simulate how the photons couple via the dust to the gas, and how radiatively driven AGN, but also the photons emitted from the stars couple to the gas and then drive a wind. I'm doing this in idealized simulations with a relatively high resolution. It's debatable. And I use zinc particles that represents clusters of stars that have their own individual stellar population associated with them. And each of these stellar populations then follow their own individual stellar evolution tracks that then emit photons or explode then at the end of their lifetime into a supernova. So just quickly a little bit more. So these zinc particles accrete mass. For each 120 solar masses of accreted mass onto the zinc particle, I then draw an individual stellar particle that is associated with the zinc particle. These stellar particles then follow their own evolution tracks, and at each time step within the simulation, I then emit radiation calculated from an individual stellar spectrum extracted from starburst 99. And then at the end of their lifetime, the stars then explode into a supernova where I inject momentum or energy depending on whether I have the cooling radius resolved or not. So this is, for instance, an example of one of these spectra from which then I calculate the amount of photons I have to inject into each photo group. So I use 3 different UV photo groups that are bracketed with the ionization fraction of hydrogen and helium. Okay, so this is one of these idealized simulations. So they start with a relatively thin disk. I tried my best for them to actually not start as thin as usual in these idealized simulations. And then one can see that the gas starts to collapse, cold gas and molecular gas starts to form, stars start to form, and they explode in supernova, and they emit their radiation. And so with time in these simulations, a 3-phase ISM starts to develop where I have these dense molecular clouds, but I also have warm gas, and I have a lot of hot gas bubbles in the simulation. So given the implementation of the model, it allows me to look at the relative impact of these individual stellar feedback channels and what effect they have on, for instance, the composition and the properties of the ISM. And so this is this one illustration of this. So on the left-hand side, you can see the simulation where I don't have any stellar feedback, and you can already see that even without any feedback and just gravity and cooling alone within this simulation, I already start to get a very structured ISM actually, but a lot of cool and cold gas. And so the supernova then shown in the middle of this panel then start to disrupt this cool gas and start to heat up the low density gas, and a hot gas phase starts to develop. And now when I include the UV radiation or the radiation from the stars, they start, so it's basically a pre-supernova feedback. They start to disperse the high-density cold gas surrounding the star particle. It increases the warm volume filling fraction and starts to change actually the structure of the ISM, mostly in the cold and the warm fraction. So this is also shown here when I look at the volume filling fractions within different regions of the galactic disk. So they basically trace different surface densities within the disk. And what you can, so on the left-hand side, you can see the supernova. the volume filling fraction in different regions of the disk for the supernova run. And on the right-hand side, you can see the volume filling fraction within the different disks for the supernova on the radiation run. And so what you can see, first of all, is that the volume filling fraction of the cold gas decreases, right? Like the blue bars start to decrease, and the volume filling fraction of the warm gas starts to increase because the UV radiation disperses the cold dense molecular clouds, or starts to disperse the cold dense molecular cloud and increases the warm volume filling fraction. So this then has obviously an effect on the star formation within the disk. And this is mostly because the ambient supernova density of these stars is reduced. And that means that the effect one supernova can have in driving a large-scale winds is enhanced because of the lower ambient density of the star. And so this is what is shown here. So this is the log surface star formation rate as a function of time for the 3 different simulations. And what you can see is that when you include the radiation in the simulation, the star formation rate is reduced by a factor of 2. So it has an effect also on the star formation rate, the global star formation rate within the whole disk. If you then look at where exactly actually the UV radiation, at least in my simulation, has the biggest effect, you can, so I show here again basically the surface density of the star formation rate as a function of time for these individual disks. So they trace different trace different surface densities within the disk, and what you can see is that the biggest effect when including the radiation is in the center of the galaxy, where we have the highest surface density and therefore also the coldest and densest gas. And this is where really the UV radiation has the biggest impact by starting to disperse the high density and the cold gas in the ISM. So the UV radiation doesn't only have an effect in influencing the structure or the composition of the ISM, but also the energetics of the ISM. And this is shown here by looking at the specific energy power spectrum for the different simulations. So on the top panel, you can see the power spectrum of the no supernova simulation, on the right side for the supernova simulation, on the bottom left panel, the supernova plus UV simulation, and on here the bottom right hand side is basically the ratio of the simulation where I include the radiation over the simulation where I don't include the radiation. And so it's quite a complicated slide, and so I just want to point out a few things. So first of all, one important takeaway is that only when including supernova feedback, I get a turbulent phase in the warm gas phase in the ISM. So this is illustrated here in the top panel, and top right panel, where I get a turbulent power spectrum in the warm phase only when I have supernova feedback. And the second point I want to take home is that if you include radiation, you start to increase the specific kinetic energy at many scales in the warm gas, and you decrease it on many scales in the cold gas. So these different feedback processes also obviously have an effect on the energetics of the gas within the galaxy. And so why am I interested in this? It's also because these different compositions of the ISM have an effect in how efficiently the AGNs couple to the gas and then drive a large-scale winds. And so this is what I want to talk about next. So first of all, there are 2 different modes of AGN feedback, illustrated here by observations of Russell et al. So on the x-axis, you can see the expected mean accretion rate of different observed sources scaled by the Eddington luminosity. And then for each source, you can see 2 dots. So one dot is the blue dot is the power of the cavity, so basically the mechanical power of this source scaled by the Eddington luminosity, and the red triangle is the radiative power of this source scaled by the Eddington luminosity. And so on the left hand side is basically low accretion rate onto the black hole, and on the right hand side is high accretion rate onto the black hole. And so what you can see is that at low accretion rate, the mechanical power dominates over the radiative power, and at high accretion rate, the radiative power dominates over the mechanical power of the accretion onto the black hole. And so that's one of the reasons why many of these cosmological simulations start to invoke these two modes of AGN feedback, depending on the different accretion rates onto the black hole. So yeah. Here. Yeah. I think they have done that in that paper by using the bulge mass black hole mass relation. Yeah. Okay. So how is this AGN feedback supposed to actually regulate the evolution of these massive galaxies? And it's basically done in two ways. So first of all, AGN feedback can suppress the accretion onto the galaxy by heating up the CGM and injecting turbulence, but it can also eject gas from the galaxy and influence the gas within the galaxy. And with these idealized simulations that I'm doing, I can basically look at the second question, or the second way of how AGN feedback influences the evolution of these massive galaxies. So I can look how these AGN feedback modes interact with the ISM and how they affect the gas structure within the ISM. So what I'm interested in is exactly how these different AGN feedback modes couple to the ISM, which, for instance, if I have a radiatively efficient AGN feedback, which photo group is important in driving a large scale winds, how does that happen locally, and how does it propagate through the ISM out to larger scales? So how do I do this? I do, again, radiative hydrodynamical simulations with 5 different photo groups, so infrared, 1 optical, and 3 UV photo groups. Again, the UV photo group, they bracket nicely the ionization fractions of hydrogen and helium. And then I inject at any given time the average photo density energy within each photo group. And I have done like simulations, very idealized simulations, kind of toy models, if you want, where I set up three different ISM models, and I really just basically looked how these photons couple to the gas and how they drive a large-scale winds, and how efficiently they do it, depending on the different ISM properties that I set up in this very idealized way. And so I show this in 2 plots. So first of all, on the left-hand side, you can see that you can see a plot where I measured the rate of change or the momentum change as a function of time, scaled again by the input momentum. So and then it's the log. So if it's above 1, you basically have a lot of photons that are scattered in the optically dense gas, and that drives the large scale winds. So that's one important part, that these photons, these infrared photons, they can gather in the optically thick gas, and they impart a lot of momentum into these into the dense gas. And then on the right hand side, I then calculate the coupling efficiency, how efficiently these photons actually couple to the gas, and this coupling efficiency is well below 1. And why is that so? This is because of the non-uniform structure of the ISM and the building of these low density channels through which the photons escape, and you get a loss of momentum that then leads to a lower coupling efficiency lower coupling efficiency that usually is actually used in a lot of the cosmological simulations. And this is really because of the non-uniform structure of the ISM. And this is why I think it's so important to actually also look at or to include a property, a stellar feedback regulated ISM, if you are interested in how AGN feedback couples to the ISM and drives a large scale wind. Why should I also simulate, for instance, a mechanical driven wind? So why should I look at the two different modes of AGN feedback and how they couple to the gas? So this is demonstrated here in this plot. So on where I show basically the velocity as a function of the density for 3 different times within the simulation, on the top for a mechanically driven wind and on the bottom for a radiatively driven wind. And the takeaway message from this plot is basically that these 2 different modes of AGN feedback couple to the gas in a different way. First of all, the mechanical wind, it basically starts first driving the low density gas and drives that to large velocities and out of the galaxies. There's the radiation, the photons, they actually first couple to the dense gas via the infrared scattering. And drives this way a large scale wind. And this illustrates that these different 2 modes of AGN feedback couples to the ISM locally in a different way, and that potentially also then has an effect of the amount of gas, for instance, in these large scale winds that then later on interact with the large scale circumgalactic medium. Sorry. Okay, so now I talked a lot about these idealized simulations, these idealized ISM simulations. Obviously, massive galaxies, they don't live in isolation. They live in a large-scale environment where these large-scale or the launched large-scale winds then couples or after it moved through the ISM, couples to the circumgalactic medium and interacts with with the inflowing gas as well. And so this is why I'm going to show you another simulation set that I'm a PI of, the SURGE simulations. They're cosmological zoom-in simulations of different galaxies in various different mass ranges, ranging from dwarf galaxies to massive galaxies. They're simulated with the moving mesh code ARIPO. We use the ARIGA galaxy formation model that uses an effective equation of state. So really the ISM within the galaxy is treated in a very approximate way, completely different to the simulations what I presented before. It includes gas, stars, and black hole, as well as dark matter. It also has ideal MHD, where we see the small uniform seed field in the simulation, a turbulent dynamo at the beginning of the simulation starts to develop, and the magnetic field strength is realistic compared to observation at redshift 0. One large unknown of how these large scale winds also interact with the CGM and how they affect the properties of the CGM are actually also cosmic rays. So I also simulated all these galaxies, including cosmic rays. The cosmic ray is solved using a gray approximation. So basically, one energy density for the cosmic ray. It's evolved where the proton cosmic ray energy density is evolved per cell basis. We use anisotropic diffusion along magnetic field lines. We have hadronic and Coulomb losses included, as well as Elfine cooling. And so I started to explore the effect of the cosmic rays within these cosmological zoom simulations fairly recently. So I'm going to show you very preliminary results. I don't have the answers to the whys for all the questions yet, but let's see. So here on the left-hand side, you can see for 4 different mass ranges. So for 10 of the halo, so 10 to the 10 halo, ranging up to 10 to the 13 halos. the density structure, including no cosmic rays on the left-hand side, and the density structure including cosmic rays. And one thing you can see, I hope, is that the cosmic rays, they influences the sizes of these, of the disks. They influences the sizes of the disks, and therefore have, in some sort of form or shape, have an effect in the angular momentum distribution, either of the gas that flows into the galaxy, and therefore it changes somehow the angular momentum within the disk, or it has an effect on where the stars within the disk are actually formed, whether or not they're formed in the center or in the outskirts of the galaxy. And with this, it has an effect on the angular momentum within the disk, and that then influences the sizes of these galactic disks. So I don't understand yet why, but somehow the cosmic rays influences the sizes of these galactic disks, mostly for the lower mass galaxies. Yes. 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 So I don't have photons in these simulations. So I don't have radiative transfer in these simulations. I do have a way of simulating how these charged particles interact with the magnetic field, how they then have a cosmic ray pressure, and how this cosmic ray pressure then accelerates the large scale winds or out to larger scales. So that I have, but I don't have radiation in these simulations. Yes, it's a different type of approach. Yeah. So they do have an effect in the sizes of the galaxies. They also have an effect on the star formation rate within the galaxies, mostly for the low mass galaxies. So for galaxy sizes lower than the Milky Way mass. So you tell me how much time I have. Yeah.
So do I understand correctly that these cosmic rays matter only in combination with the magnetic field? So is it because they are charged, or is it?
No, they interact with the gas via the magnetic field.
But if you wouldn't have magnetohydrodynamics,
I can't. Sorry, Robert. So I can't, this does not, like, I don't know how they only evolve if how I have to evolve the cosmic rays, I only know if I have a magnetic field, because they're connected. They only diffuse across. Yeah, exactly. But I have the charged cosmic rays, so they only diffuse. The anisotropic diffusion is along the magnetic field lines.
So the answer is yes.
So what? So say again the question. I don't know what I should answer yes to.
Whether they act via the magnetic field or because.
Yeah.
Yes, so you need, of course, the physical level, you need to feel that, of course, people have that running simulation of the possible without fields, then of course
yeah, that's true. The full effect. And they're like, I mean, cosmic rays are quite complicated on a plasma level. So many things are actually fairly unconstrained if you look at the cosmic ray physics on a plasma level, and so you can argue whether or not the anisotropic diffusion or the diffusion has the biggest effect, but within our approach, let's say, the anisotropic diffusion is important in order to drive the wind and affect the CGM. Yeah, that's what I can say. Okay, so then how these cosmic rays affects the thermal state of the CTM. So again, for these different halo masses, I show you the temperature scaled by the virial temperature within the halo, and what you can see is that indeed for the lower mass galaxies, the CTM properties are actually quite changed, and are actually quite changed, and they increase the temperature within the CTM, and by doing so, because the density is not changed by much, so basically that means that the pressure within the CTM is also changed, and that then has an effect of how these large scale winds then propagate out to larger scales. So this is a very preliminary plot of the radial velocity in these lower mass galaxies. For on the top there is no cosmic rays, and on the bottom there are cosmic rays. And what you hopefully can see is that the cosmic rays also increase the radial velocity of the gas, of the outflowing gas within the CTM. Yeah, so as a conclusion, cosmic rays become less or more important for less massive galaxies. There are a lot of caveats if you actually look at cosmic rays physics. So one is that I don't include the cosmic rays from AGNs that may actually be important for massive galaxies. And again, as I already said, like on plasma physics level, cosmic rays are extremely complicated and poorly understood and constrained. So this is I guess one caveat. So what is my road to the future? Hopefully, so I presented you very idealized simulations and large-scale cosmological simulations. Obviously, in some sort of way, I would like to connect these two different complementary approaches of doing simulations, where I let the large-scale simulations be informed by the smaller-scale simulations, and potentially vice versa. That is my road, hopefully, to the future. Yeah, and I'll leave you with this. Thank you.
Questions?
Go ahead.
So this is a really nice picture. Where is the biggest challenge? Maybe the single biggest challenge.
The single biggest challenge. Whoa. I mean, okay. Again, like it always depends at the question you're interested in. If you're interested in how different, well, okay, can I say two? If you're interested in how different stellar feedback channels couples locally to the gas, the physics and the chemistry of molecular gas is largely not understood, and the formation of the stars within these molecular clouds is very complicated and is a big challenge. So that's one. And then if you're interested in the AGN physics, I mean, AGN physics is largely actually not understood on a fundamental physics level. So how exactly the spectrum, for instance, coming from the accretion disk surrounding a black hole is not understood. How exactly, whether it's line driving that like drives the mechanical wind from the AGN, it's all not fully understood. So everything around AGN is also a challenge. Yeah, yeah, I would say.
Questions? I could ask a question. Several actually, but one of the things I didn't understand was you guys think about questions while I ask. Was this you showed this plot? I know it's not probably not your plot, from the observations of mechanical versus radiative.
Yes.
So how is mechanical feedback or mechanical outflows measured then? How's that even possible?
So so it's not my paper. So if I correctly remember what they do, so what you can do is you can look at the sizes of these cavities, for instance, in clusters, from AGN jets, and then from these sizes, you then can you defer a power that must have come in order to create that cavity, and that's how they calculate the power of the cavity, or the cavity power, the mechanical power that must have gone into creating this cavity.
Okay.
Okay, so I have one second question.
Yeah.
So at the very beginning, like, you talked about the importance of the radiation. Right?
Yes.
And this radiation. Yeah.
Mm-hmm.
Maybe I missed it, but I think you essentially talked mainly about like radiation pressure. You also effect of the radiation.
Good point. So first, a small correction. So for instance, for the radiation from the stars, there is radiation pressure as well. So direct radiation pressure, but also radiation pressure from the multi scattering in the infrared. But what actually mostly drives the wind is not, at least in my simulations. I know that other people have different opinions, but at least in my simulation, it's not the radiation pressure that actually drives the wind, but the coupling of the UV photons, the heating then of the gas, and that then drives the wind. So just like a small correction. So that, and then I don't include, that's one thing that is actually, I don't include, well, I have non-equilibrium cooling, but I don't have various cooling lines or coolants in my code. Yeah, I have non-equilibrium cooling of hydrogen and helium, but obviously the radiation would also impact the formation of different molecules in the dense gas, and I don't have that included. That's definitely something that somebody should be doing at some point. Yeah. It's very complicated because I mean, for it to also be converged, because you need very high densities to actually really resolve properly the formation of the molecules within the molecular gas. There's no such thing. That's what you told me once. Yeah.
Basically, of the barrier, the kind of
Mm-hmm.
so does the separation tend to already actually
Good question. I actually don't know at the top of my head the relative importance of both. Especially so for very massive galaxies, the effect of AGN feedback, the most important effect of AGN feedback is actually in suppressing the accretion onto the very massive galaxies. Many people think, and for the dwarf galaxies, the biggest effect is mostly from the stellar feedback and basically driving out outflows rather than halting the accretion onto these lower mass galaxies. And it must somehow, this importance of whether or not accretion and or expelling must somehow change within the Milky Way mass range, but I don't know for sure. I need to check that actually. Yeah.
I have another question.
Yes.
So where does this all stop? Do we have We have all kinds of feedback here. We
Yeah.
have stellar feedback, AGN feedback, current, radiation pressure, etc. And now we also have cosmic rays. That frustrates me enormously. So, okay, let me start with this.
It frustrates you because you're interested in a different question. It excites me because there's a lot of physics.
Could it be, you said it's fairly unconstrained cosmic rays. Could it
Yes.
be that it's just dominating the feedback? That is really, really strong, or is it?
Well, I say relatively on a plasma physics level is relatively unconstrained, right? But you do have so what you do have is, for instance, gamma ray observations that you then can compare to. So you can do you can again, like you need like using assumptions, but you then can compare the from the simulations, the gamma ray spectrum, for instance, in the simulations with observations. For instance, you can compare the magnetic field strength within the disk, but also within the CGM compared to observations. So whatever has to come out, right, has to somehow match with observations. So the observations are your guideline in a sense, in order to constrain as well, like potential cosmic ray parameters, at least within the simulations that you're using.
But you said you didn't use the gamma rays. It's about charge particles.
But you can,
assume a ratio with gamma
yes, yeah, exactly.
That's where
So you can, and a steady state approach, and then you can compare to gamma ray observations. Yes.
So do we need to care about cosmic rays then?
I mean, it depends who you talk to, right? I think this is largely not yet a fully answered question. I think you should care about cosmic rays. Okay. In our simulation, right, the cosmic rays have an effect in the lower mass galaxies, not so much in the higher mass galaxies. There are different simulation approaches. For instance, the fire simulations, for they get like a slightly different answer. There are also even more idealized simulations of stratified disk simulations that also get like a more a similar answer, that in the Milky Way, at least, the cosmic ray don't have an effect, or like Milky Way, they don't have an effect in the mass. Well, they don't have an effect on the star formation, but they do have for instance, an effect on the mass loading of the wind, things like that. But it's I guess work in progress. Yeah.
I think we have the opportunity to ask questions later on and throughout the year.
Half year.
This is one floor up, right?
Mm-hmm.
So, and I think you guys are going out for lunch, so that's also an opportunity. So let's thank Rebecca again.
Thank you. Thank you. So did you stop? Yeah.